So if I am going about trying to solve a differential equation, it's possible that the differential equation that I'm given will not have a solution that I can find that I have a method for, an analytic type solution. Possible that would happen. Well, you've got a couple of things you can do. First thing you can do is if you could possibly draw a direction field to get an idea, or create with a computer or some type of calculation device, create a direction field that might help you get pinned down a path of a solution curve. Or if you had an initial value, you might could do a numerical approach to it. And the numerical approach we're going to talk about tonight is called Euler's method. And we talked last week that a derivative is the slope of a tangent line, or it represents a slope. So what we can do is create a curve by connecting different little slopes of line segments together. Let's say I start with an x coordinate given to me, x of 0, given. And we'll say that corresponds to some point up here, we don't know, y sub 0. So if they give you a couple of things in the problem, then you can use this method. The first thing you're going to have to be given is the actual differential equation itself, y prime in some term of a function of x and y. You'll have to be given your differential equation. And we talked about this a little bit last week, an initial value. An initial value. So that's my point right here. Now what you're wanting to do here is to create little line segments defined by this differential equation that will map out a possible, let's say I do a step size, I'm going to add just, let's say, 1 unit to that x. Add 1 to it. So what you're wanting to do is say, where would this point map? Possibly a point up, so the slope of that line segment, possibly another one later on, another line segment, and so that would map out kind of a solution curve to this DE. Now what was the most basic definition of slope that you guys remember from algebra class? I think I heard it. Say it. Rise over run. You got it. Okay, so let's pretend that I've got another coordinate plane situation going down here. Okay, and here's my x sub n. Now here's another point, x of n plus 1. That's your next x coordinate. We're going to say that x sub n is going to correspond to a y sub n. And on up here, we're going to have a y sub n plus 1, your next y. Okay, from across the x-axis, from one point to the other, the x point, that's called a step size. How are you going to step this out? How are you going to add to each x coordinate? If you're going to add, are you going to add 1 to each x coordinate? Are you going to add 0.5 to each x coordinate? How are you going to step this out in your process? The trick is, the smaller your step size, the more accurate your curve will be. But you have to be given that. If you're going to do a problem, you have to be given what step size to use. Okay? So, the distance from that point to the other, we're going to call that, let me do that in a different color so you can see it. We're going to call that h. That's the step size. Okay, and then that's the run, correct? The run is h. How much you go over. Okay, And then you're going to have an amount of rise. Well, let's talk about how that would look like. Your amount of rise would go going up from y sub n to y sub n plus 1. I don't know what to label that yet. But we know that together the run and the rise represent the slope, right? So the slope, we're going to talk about the slope being this diagonal line right there. This is going to be the slope. Now, Euler's method uses the notation for your differential equation, big A sub n. So what we're going to call this side right here, the slope side, we're going to call this big A sub n. I want the slope to actually be that differential equation A sub n. So what I need to get to make that, this rise part, we're going to say that the rise is h times A sub n. The step size times your differential equation. So if you have that, then you algebraically can see that the slope is represented by your differential equation. Now, if I want to know what the next line segmented slope that will be attached to this one right here, going up or going down or however it goes, according to my differential equation, what I need to do is use Euler's method. This is Euler's method right here. Your next y, or y sub n plus 1, is equal to your first y, y sub n, plus, how much did we go up here? We went up h times A sub n. This is Euler's method formula right here. Some of y'all might think that that's called Euler's method, but it's not. Euler's how you say that. Y'all probably have learned that somewhere down the line. Euler's the guy, remember, that did E. We learned how to do E, the function E. He's the one that invented that. So y sub n plus 1 is equal to y sub n plus the step size times the differential equation. The A sub n, remember, is the dE that's given to you. You have to be given an initial value in the problem, and you have to be given the step size to use. This is the part that you're going to code. This is what you're going to code in Excel to use. If I say do it using Euler's method, this is the rule we're going to use. So keep that, highlight that, use that to set up our problems in just a second. Let's do a problem. And I want to write that Euler's method rule down again to kind of help me remember it as I go here. Y sub n plus 1 is equal to y sub n plus h times A sub n. That's the rule we're going to use. So here's a problem. It says use Euler's method to approximate y of 0.2. Y of 0.2, given that y prime is equal to x squared minus y squared, so they gave us the dE, that's your differential equation right there. Where y of 0 equals 1, that's your initial value. X is 0, y is 1. Using a step size of 1/10. So 0.1 is going to be your step size here. Okay? So let's kind of set us up a chart. We're going to use Excel later, but right now I want to get this in our head, how it works. We're just going to do it by hand. Okay, so I have my x sub n, my y sub n, my h times, actually let's do it this way. X sub n, y sub n, a sub n, and then h times a sub n. This is going to kind of help me do every the steps out in the right order and help me do this. Okay? So what you're going to start off with, what do you think we're going to put in the first x of n blank? What are we going to put there to start us off? 0. How'd you get that? Y of 0 equals 1. That's your initial value. Initial means at the beginning, right? How do we start out? Your initial value. So 0 is going to be my first x. What's my first y sub n then? 1. Easy first two blanks. Okay. A sub n. Y'all remind me what a sub n was? The differential equation. So your a sub n in this problem is x squared minus y squared. So x squared minus y squared, I actually need to do it numerically. We need to do x squared minus y squared. So in this problem, what is 0 squared, calculator time I guess, maybe, 0 squared minus 1 squared. What would you get if you calculate all that out? Don't go any further. Stop right there. Do y'all see? Does everybody see here? I got the negative 1. Just doing the math, right? X squared minus y squared. Okay. Easy step. Next thing is the step size times a sub n. So what was the step size for us? 0.1. So I want you to do 0.1 times negative 1. 0.1 times negative 1. Tell me what you get. So you get negative 0.1? Easy arithmetic, right? Okay? Next step. The step size, if you'll remember, is how x grows. So what is my next x sub n? 0.1. You're going to add your step size each time to your x. That's how the x grows, by the step size. So 0.1. So in this second blank right here, it's the first time we're going to do Euler's method. So I'll make a little mark here to let me know that's what I'm going to do. Okay, so I need your calculator. And guess what? The teacher is being irresponsible and doesn't have his calculator. Is that what they do? Okay, so y sub n plus 1, that's that next blank. You're going to do y sub n, so that's going to be 1 plus your h times a sub n. That was whatever was in this blank right here, right? So 1, your y sub n, plus this, plus 0.1 negative. So we get what, 0.9? So to get this y sub n, this is your y sub n plus 1 right here. You're going to use Euler's method. You're going to say your previous y sub n, which was 1, plus h times a sub n, which was this previous blank right there. So 1 plus negative 0.1 gives me the 0.9. All right, so what do y'all think I'm going to do right here? What are we going to do in this blank? We're going to go back to x squared minus y squared, right? But you're going to use your new x and y. Your new x and y. So you're going to actually type in 0.1 squared minus 0.9 squared. 0.1 squared minus 0.9 squared. And I've got the answer there. What'd y'all get? Negative, right? Y'all are correct. Good job. Negative 0.8. Okay, so next blank. the step size? 0.1 times negative 0.8. Right? 0.1 times negative 0.8. So negative 0.08. Okay, let's go down one more. We're almost done with this problem. We almost solved it. What's my next x value? 0.2, because you're just going to add your step size again. 0.2. Okay, now Euler's method again. This is the hard step, remember. So y sub n plus 1, one more than this one, is going to be your previous y sub n. So 0.9 plus negative 0.08. 0.9 plus negative 0.8. Tell me what you get. Okay, and we have actually answered the question. Okay, you're done now. Because look what the problem says. Use Euler's method to approximate y of 0.2. Well, where's y? X, that's x being 0.2, right? Y of 0.2, the x is actually the 0.2. So when x is 0.2, what is your y value? 0.82. On the test, that's the kind of question exactly you're going to have right there. I give you the DE, I give you the step size, I tell you the initial value, you tell me what the approximation, I'm going to ask you to approximate something. Okay? Now, you're saying, well, how would that graph a solution curve? Can anybody look at the chart and tell me how you might be able to graph a solution curve now? Even if you had a direction field, you can still graph in that direction field. You may tell me what you think. This is an approximation too, by the way. Well, how would you know how it would curve? What would you plot? Your points. Plot the point 0, 1. Plot the point 0.1, 0.9. X, Y, X, Y. Plot those points in the graph, and then see how the fluidity of the curve goes. We're going to actually graph them using that step. Okay? But that's how you could, point by point, draw your solution curve. Now, that's going to get even more accurate the smaller you make your step size. Okay? So if I half that step size, yeah, I would have to do double the amount of steps to get there, but my answer is going to be more accurate. Let's do another one. Actually, let's talk, before I do another problem, let's go ahead and learn this next thing. Modified Euler. Improved. Those are a couple of titles that have been given. Hoyne's method. That's another name of this method. And one more that you might see in an engineering book or something is the Runge-Kutta. Method. Those all kind of mean the same thing. We're going to take Euler's method and expand on it a little bit. Okay? Make it possibly more accurate. Now this is what you got to use for the here's improved Euler's method. Y sub n plus 1 equals y sub n plus h times the average of two differential line segments, A sub n plus B sub n divided by 2. This is a little complicated to think about. I'm going to try to help you, do my best to help you kind of understand the parts of it. Kind of looks like original Euler's method, but that second part there by the H is kind of weird. You got two differential equations going. Everybody knows what A sub n is, pretty easy. B sub n is kind of like a temporary differential equation we're going to use other information with. So let's think about this for a second. We're going to talk about a y sub n plus 1 temporary. This is going to, I'm going to put that little mark over it. That just going to mean this is going to be some kind of weird, different Euler's method kind of deal. Y sub n plus 1 temporary, we're going to say is like the original. When I start doing these, I really have to get my mind right, or I can figure out how to code it and that kind of thing. Then, B sub n, if you're trying to define what the B sub n is that you're going to plug in right here, B sub n is actually a new function, a new differential equation, where your x is the next x. Not the one that you previously worked with, but the next one in line. The next x coordinate in line. X sub n plus 1. And the y value comes from your y sub n plus 1 temporary. The y is coded with this formula. That's crazy, I know, but if we practice it for a second, you'll kind of get it better. B sub n is a new differential equation that you make up using your next x value and this y sub n plus 1 temporary. Weird. Write that down, though, and I promise that maybe it'll make sense in just a second. Now let's do a problem, and let's do it first with the original Euler's method and then with the improved Euler's method. Okay? Do it both ways by hand, and then we're going to get on the computer and work a little bit. Make show you how much easier it can be. All right, let's see. Good. Okay, here's what we're going to work with. Let's start off with this little easy differential equation. Y prime equal to 2xy. That's your given dE. Your initial value is y of 1 equal to 1. That's my initial value. And step size we're going to use is h equals 0.1. We're going to use 1/10. And we want to approximate, let's do it really easy. Let's do find y of 0.3. Y of 0.3. I'm sorry, 1.3. Okay, so we're going to first do original Euler. So we're going to start out with 1, 1. Now my step size is 0.1, so we're going to do 1.1, 1.2, and then lastly 1.3, which is what we're trying to find. So we'll stop with this blank right here. That's where we'll have our answer. Okay, so your differential equation that you're given, and man, I need my calculator. Okay, 2 times x times y. 2 times 1 times 1. What's that give me? 2. Next blank. the step size times your differential equation. So 0.1 times 2. Point 2. Okay, so in the first blank here, that's the first time we're going to do Euler's method to find y sub n plus 1. Does anybody remember what the formula is? I forgot to write it down here. Y sub n plus 1 equals y sub n plus h times a sub n. Okay? So in this case, it's going to be 1 plus 0.2. $1.2. Okay, carry on, people. Okay, now that I got my calculator here, let's see here. A sub n on the next level, this next blank. A sub n, I'm going to use the next two x and y's right here, then two new x and y's to plug into my original differential equation. 2 times x times y. 2 times 1.1 times 1.2. And I got 2.64. Multiply 2.64 then times the step size. So times 0.1 equals now, my new y sub n, remember you do Euler's method to get that. Get your new y sub n. So in this case, it's going to be 1.2 plus h times a. So this blank right here, 0.264. No. 2 times x times y. That one you're saying is that other problem. This is a new problem altogether.
Oh, okay.
Your a sub n is the dE. Your a sub n is the differential equation. This is a brand new spanking problem. Okay? Totally depends on what you're given. So this right here is 2 times x times y, so I got to do 2 times those two values multiplied. It is kind of number crunching and boring. 2 times 1.2 times 1.464. I got 3.5136. So we're almost done. 3.5136 times the step size. So 3.5136 times 0.1 gives me this right here. So last time, and I'll have the answer to what I'm asked for right here. You're being asked for y of 1.3. So the last iteration we're through. We're going to do Euler's method one more time. 1.464 plus this h times a sub n column right here, 0.35136. So I got 1.81536. So approximately y of 1.3 is equal to 1.81536. And that's using just regular old Euler's method to do it. On the test next week, I'm going to give you one question like that. You shouldn't have to do more than 2 or 3 iterations of it. I'm not going to make you kill yourself trying to fill out that chart. Is everybody seeing where the numbers are coming from? kind of, sort of, maybe. And then, of course, you could plot those ordered pairs and you map out your solution curve also. Now, improved Euler's method is supposed to be better. It's supposed to be a more accurate depiction. Let's do this same problem, exact same numbers, but let's do it with improved. And let me show you the difference. This is really weird, okay? And I want to do one by hand before I do the computer because I want you to see where everything's coming from and how the parts are come up with and that kind of thing. So again, I'm using that same problem. Y prime equals 2xy. Y of 1 equals 1. That's my initial value. We're going to use the same step size. And we want to find y of 1.3. I may regret that. I may be wishing I'd say 1.2 because this can get hairy. Same problem I just got through doing. So we're going to start out like we did, 1 and 1. Oops. Okay. So, first and foremost, what do I fill in right here in a sub n? It's just your regular differential equation, right? So 2 times the x times the y. So 2 times 1 times 1. Yay, no problem. Okay, here's where it gets weird. Let me write this on the board over here to kind of help us remember our stuff. Well, I'll do it right here. Y sub n plus 1 temporary is y sub n plus h times a sub n. B sub n is a new function, a new DE, where your x n plus 1, you use the next x that you get, and you use this y sub n temporary as your y. So I'm going to write this in for this first code. This is equal to 2 times your next x will be 1.1, right? Your next x won't be the same one on this same line. It's going to be the next x, okay? Times your x will be the 1.1 times your y sub n plus 1 temporary. Well, we got to figure that out. Y sub n plus 1 temporary is all this stuff right here. Y sub n plus 0.1 times a sub n. So let's try that on our calculator. 1, your y sub n is 1, plus 0.1 times a sub n, which was 2, equals 1.2. Okay, a little bit hard to do here. Let me write this out here. how you're going to do your B sub n. What do you get there when you multiply that together? 2 times 1.1 times 1.2. What'd y'all get? 2.64? Me too. Okay. First time I have to do improved Euler's method is right there. It is y sub n plus 1 equals y sub n plus the step size times the average of an and bn. So it's a little bit complicated to plug in. Let's think about it right here. It's going to be 1, your y sub n was 1, plus 0.1 times, I'm going to use my parentheses keys here. Open parentheses. 2, open parentheses. Let's see, how do I need to do that? To punch in my calculator, y'all might have a better calculator. Mine might do better to do this part first. And then add that. So let's see here. 2 plus 2.64 equals, divided by 2, equals. And then times 0.1 equals. And then plus my y sub n. Tell me what y'all got on your first one. That's what I got. 1.232. That's going by this formula right here. It's going to wear me out, I can tell. Making sure y'all know which way to go. Which way did he go? Right here, a sub n on this line right here, you're going to do 2 times x times y. You're going to find out real quick why we like the computer better. 2 times 1.1 times 1.232 equals 2.7104. Okay, here's the hard part right here. Keying in this one. I think I'm going to do this one backwards too, entering it in my calculator backwards. Let's do this big chunk right here. Y sub n plus h times a sub n. So let's see what here. Y sub n is 1.232 plus 0.1 times 2.7104 equals times this x sub n plus 1, that's your next x sub n, so 1.2 times 2. I got the same thing I got last time I did this problem. Anybody get an answer on that one? Yes, ma'am. It comes from your DE, whatever's right there. The constant will stay the same. The x changes to the next x, and the y changes to this whole big glob of stuff right here. Every time, that's what happens. Like I said, when we do on Excel in a minute, you'll code it one time, and then you'll drag your column down and it does it perfectly for you for the rest of the whole problem. It's just you get that first coding right. That's what you got to worry about. But yeah, it depends on whatever the DE you were given was. Constants stay the same, x's change, y's change. Oh, okay, we got a couple more times to go here. Let's see what we got. Y sub n, that's the next time we do modified Euler. So I'm going to go backwards with my calculator. I think it'll be better. So I'm going to average a sub n and b sub n, divide those by 2. So let's see what I got here. 2.7104 plus 3.607296 equals, divided by 2 equals, times the step size, so times 0.1 equals, and then add my previous y sub n to it, so plus 1.232 equals. Anybody got an answer for that one? You're with me if anybody else is or not. Is anybody lost in this? This is awful. To me, my eyes are about to cross. You've got to make sure you're going step by step like you're supposed to. Okay? So a sub n, let's do it again. We're almost through. 2 times x times y. 2 times 1.2 times 1.54788848 equals. Mr. Smith, do we have to put that mean decimal places? I'm going to, just to make sure my calculator is right. Okay, this is the hard one right here, b sub n, so I'm going to go backwards again. So y sub n was this 1.54788848 plus 0.1 times the a sub n, which was the 3.71492,352 equals, okay, times x next, 1.3 times 2. Did anybody get an answer for this blank? Okay, thank God. We're just one more blank and we've got our answer. If you're really geeky and nerdy like me, then you like this, okay. But I'd rather be at my desk sitting comfortably, punching numbers than standing up here stressed out because I'm like performing for you guys. That's what I feel like. Because this is so hard to keep straight. Okay? So my last time with improved Euler's method, I'm going to follow this rule right here, and I'm entering mine backwards because it works better on my calculator. So average the a sub n and b sub n together, 3.71492,352 plus 4.990380,595 equals, divided by 2 equals, times the step size, so times 0.1 equals, and then plus your previous y sub n, so plus 1.54788848 equals. How much did this change it by? A good little bit, didn't it? With regular Euler's method, what did we approximate 1.3 to be? So there is some error there in between the two methods. 1.81 to 1.98, there is some error. But this is supposed to be your better method. This is supposed to be your better method. Okay, so let's do fun. Everybody on your computer find Microsoft Excel. It is under, when you can pull up all programs. Do we have computers ready to go either, by the way? I'll make mine bigger so you guys can see it better. Okay? As you know, your variables this time are going to be cell names instead of, you're not going to put an X in there or a Y in there. You're going to call it by the cell it is. Okay? So let's just look at that problem we just did. The same one that you just did. Your y prime is equal to 2xy. Your initial value is y of 1 is equal to 1, and your step size is 0.1. So if I want to do, I'm going to name this first curve. I'm going to say this is Euler's method. Okay, and in my first column there, I'm going to name that one x sub n, y sub n, just like I did on my paper, a sub n, and h times a sub n. This is just headings and labels. So what are we going to enter in the first column? Your initial value was what? Y of 1 equals 1. So we're going to put a 1 first column, a 1 in the second column. Okay? Now, to code this, some of y'all are way ahead of me with the Excel probably. You've probably done way more than I have done. But what I would do is just say equals in that cell right there. 2, remember our DE was 2xy, right? So 2 times, the little asterisk sign is your multiplication symbol in Excel. 2 times x. What are you going to put down for x in this problem? It's this cell. What's this cell right here's name? A3. Good job. 2 times A3 times what? Your y. What was y in this problem? B3. And then just hit enter, and it calculates it for you. That's 2 times x times y. Everybody good with that? Okay. In this one, we're just going to always multiply the step size times whatever a sub n was, right? So equals, my step size was what? 0.1 times, what was a sub n? C3? Check it with your work we've already done ourselves and say, are we right so far? Questions so far? Can I help anybody? Yes. Okay, let me pause this for a second and see what's going to